interval.
Ok, en términos de incertidumbre, el mapa de Matt Hansen debe tener una incertidumbre asociada y el mapa de Biomasa tiene que tener una incertidumbre asociada.
Sí.
Para la estimación se hace una propagación de esta incertidumbre.
Sí, es muy complicado. It's very difficult because why we can't come up with an estimate of error, a confidence interval at the pixel level with the biomass. It's very difficult for Matt, for Hansen, to come up with an uncertainty at the pixel level in his line cover change. Okay? What he can do is that he can do it at the regional level. Okay, so what is possible to do is to report at the regional level with a total error that is a result of the propagation error that you have in the biomass data plus the errors that you have in the line cover change data. You have to combine the two, and you will report a total error on the estimate of time. But we have been talking about this because we would like to do it. And yeah, I mean, at the pixel level is not possible. We might be able to do it at the regional level, but not even at the country level, but at the even larger region than the country in this case. So this is another issue, okay, that with this approach we might have.
I have a question. El mapa de deforestación de Matt Hansen trabaja bien con porcentajes de cobertura baja.
So does Matt Hansen works well with losses when the vegetation is small? Is that fair?
No, con porcentajes de cobertura
Sparse. Very sparse. In that case, it's very difficult. I don't know. It's not, it's not something that we did, and we didn't really make any effort to assess Matt Hansen data. I do know in general that deriving changes when the vegetation is very sparse is more difficult. And so I wouldn't be surprised if the uncertainty is higher when the vegetation is sparse for the changes. Because you have more signal from the background. Okay, and then the signal of the background is going to confuse with the vegetation signal. And you have to do it over time, and that would be good. Yeah, I think. But overall, I mean, Matt data, especially at on tropical level, it's a major step forward. It's great. But yes, at the country level, you guys know much better than anybody else. How it behaves. Okay, so this was a way to derive gross biomass estimate. And you can see that the detail is pretty good. I mean, when you combine the two, you can see quite a lot actually. So this approach, this data set, was used in a paper that was led by Zhang et al., where they report the biomass loss from 2000 to 2012, okay, for a series of countries. And this is one of the first times that, sort of based on people sensing data, someone reported annual changes in biomass at the national level. At the national level. Okay. Now, the case of Mexico. So, how do do we think this kind of data could be useful for a place like Mexico? Well, so one idea was, again, if you want to report at the national level, there are many ways to do it. Okay, and you don't need all to do it. But if you want to report at the national level, or even at the level that is much smaller than at the national level, then the green dots are the INFIS plot. Okay, and as you can see, and you can start to see, is that at the state level you have quite a bit of samples, but at the level that is below the state, you don't have many samples, right? Um, Here is the example, right? So at the state level, okay, but like for this region, you really have very few plots. Okay? So from a statistical point of view, yes, you can come up with an estimate, but probably your error, your confidence in this estimate is going to be pretty big. And that just is not that, that is just a matter of how many samples you have and what is the variability inside the region. Uh, so with this is you already saw this, I think, some time ago. So what we try to do as part of the MREB and was to provide a pretty much an emission factor value for each of the municipalities within each state, okay, and provide a confidence interval of the emission factor, so that you will have sort of what is the mean value of the emission factor for the municipality, but also what is the lower and upper bound of that value. And the idea here was to then compare it with the sort of uncertainty that you will get using the INFIS data at the municipality level. And the idea was, well, I mean, could we think that in some cases, probably the error from this estimate could be smaller than the error that you get from the INFIS data at the municipality level. Only because with the INFIS data you don't have enough samples in that place. And so would it make sense in this situation to actually use the estimate from the map and the INFIS data for that region, for the municipality, combine them, so that now you reduce your error and you can report at the municipality level. So this is like one way in which this kind of information could actually help. I think, but at the end of the day, it's you that you have to say yes, it helps, or no, we don't want it. We don't think that actually helps. But you can start thinking in this way, right? To sort of bring in your estimate the possibility to add data when you are lacking data. Okay? And the good thing is that for Mexico, actually, as part of MRED, MRED generated a biomass map that is based on the INFIS data. So what you bring in is not really strange data. It's driven by the INFIS data. Okay, so it will be very, very consistent. And I think that in this case, could have. Okay. Okay, so we are now ready to switch to the other section. And I just would like to sort of go over with you, for example, what are the limitations of these methodologies that I showed until now to derive Binance change, right? So some of the most evident limitation for me is that so far we are able to report on losses from deforestation only. So when you go from forest to non-forest, okay? And you're not able to report on gain. You cannot account for the growing forest that is storing over time more carbon. You can. And also, when you see your biomass loss, it's too late because it means that the forest is gone. Okay? So you cannot report on degradation. Right? And in places like Mexico, from what I hear, is that actually what I see also is that there is not much deforestation overall. But most of the losses could be due to degradation. It's not really a process of deforestation like is in Brazil or Colombia or Peru, but it is more a slow process of degradation. Here and there, single trees for firewood, for fire, or just consumption of timber at the local level, and so on. So I think it would be very important to be able to report also on degradation. Why? Because if you think about REDD, right? In REDD, in the case of Mexico, if you report on your losses from deforestation, it's very small. So you're not going to get much out of REDD because your losses are pretty small. So you just have to show that you reduce those losses, but they are already small. So payment, I'm not sure how significant are going to be. But if you bring in the degradation, and actually it's quite a bit, well then you can report on a much larger pool of losses, degradation and deforestation. And so in this case, you might actually get a more important role in the REDD assessment. Okay. So, but we said that before that it's very difficult to derive degradation because it's very difficult to identify area, to quantify the area that is affected by the degradation. So what we decided to do is let's look at things from a different point of view. Okay, let's not try to measure changes in area. We don't care about area. At the end of the day, what REDD is asking you is not change in area, it's changes in biomass, in emissions. Okay? And the reason because you measure area is because it's a way, it's a process to get to the emission. Okay? But what if you actually don't need to get to emissions? I mean, you might be interested in area change for many reasons, okay? But if it is for REDD, report on emissions, what if you don't need it, right? And so that is exactly what we're trying to do, that instead of looking at the difference between, like, a map at time one in the year 2000 and a map in 2010 and try to do the difference and try to come up with the area change, we said, no. Let's look directly at the changes in carbon density. Our carbon density in the forest, for each pixel, how this carbon density is changing over time. Let's build a time series, a trajectory of the carbon density for each pixel over the map. We sort of like to think that we were able to generate a biomass map at one time, to generate the estimate of the pixel one time, right? We did it with MODIS, we did it with Landsat, and so on. So we can do that. And then we said, what if we can actually do that every year? So that every year we have an estimate of what the biomass is for each single pixel. So then you get this type of information. Those are 3 different pixels, okay? And here on the left, what you see, the black dots are the estimate of biomass every year. Okay, so here is estimate in 2001. This is an estimate for 2002. This is an estimate for 2003. This is 2004, and so on. So you build this time series, this trajectory, no? Where the biomass is actually changing over time. And in this case, you can see that you go from 250 tons of biomass in this location, in this pixel, to about 100 in 2004. And then the biomass keeps going down over time. Now, you do see that there is quite a lot of variability in the black dots, that every year those estimates goes a little bit up and a little bit down, right? That is not real. That is just the problem that data are not perfect. Data have errors. The estimate of the biomass has a variability that is due to the noise, to the errors in the data. So in order to remove that effect, what we did is that we used this algorithm, that is a change point algorithm that fits a series of segments in the time series. And what we do is that we use the estimate provided by the blue line. Okay? So we remove the noise, the up and down. But then when we have this fitted line, we pretty much can determine what the biomass is at any time along the line. Okay? So in this way, we can report at the annual interval what the biomass is for each pixel. And this was going down, this is pretty much stable, this is slightly going up. Okay? And the fact now that you are working with the time series, you are able to be sensitive to very small changes. Okay? Because if you do the difference between only 2 points in time 1 and time 2, well, depending where these values are, you could have a huge error. It will go everywhere. But now you have, in this case, 11 points that actually constrain your estimate. You're not working with 2 points only, but you're working with 11 points. Okay, so you have a more robust estimate of what the change is. So as a result of this exercise, what you get is actually a map of changes, gain and loss. In red, in this case, I'm showing the loss. In green, I'm showing the gain. And in yellow, I'm showing what we cannot say if it is gain or loss. It's stable. What we call it is stable. It could be that there is so much noise in the data that from a statistical point of view, you cannot fit that line. You don't know if it is going up or down, so we cannot assign a sign. But the interesting part is also that not only you get a map of where the changes is happening, you also get information on the intensity of the change. You can see that the losses are from bright red to very dark red. So you have this gradient of loss, and the same for the green. You have a gradient of gain, right? Now, just for curiosity, if we overlay Mata, this is a place in Brazil, okay? This is not a place in Mexico, but later I will show some data for Mexico. So if we overlay in black the deforestation data from Matanzas, what we see is that it overlaps well with the places that are marked by dark red. So dark red is mainly where the biggest losses are. So you can think that it makes sense. Biggest losses comes from deforestation, right? But what you can see also is that around the deforestation, you still have quite a lot of red. It's not as dark as the location under the deforestation, but still you do get a lot of red. And those places are places where degradation is happening. So it's a place where it is still forest, but it lost some of the biomass that it had. So you can think that you have a forest that has 200 tons, and it went down to 150. It is still forest, so you wouldn't be able to see it with Matanza data, with the deforestation. If you're focused on deforestation, you will not see it. But in this way, if there is a decline of the biomass, even if it is still forest, you will see the decline. Okay. Yeah, this is another example in Cambodia. So we did this for all the tropics. Okay, we applied this methodology to the data set for all the tropic. The data set that changed is between the year 2003 and 2014. I apologize, I didn't update the slide. It says 2002, 2012, but in reality now we go to 2014. And we do provide an estimate of the total error on the change. So in this case, we can, for each pixel, provide the confidence interval of the error. Okay? And this is the total error. This is an error that includes the error from the allometry, from where you convert the field data to biomass and you use allometric equation, you have an error. So you take that error, then you have an error from the LiDAR data. The model that goes from field data to LiDAR is a regression model, it has an error. We take that error, we propagate it with error from the allometry. Then the next step is to make the map. The map is not perfect, it has an error. We take that error, we combine it, and we propagate that. And then we derive the change. And on the change, we have an error, and we put it all together. Okay, so it's a comprehensive, it's a cascade of errors that are combined. Just for curiosity, I'm going to show you. Here is the Xingu Basin in Brazil. It's a indigenous land. It's a protected area. Is identified by this black line. And here on the right, I'm just showing a zoom of this small part here. Okay, and the colors that you're going to see are again in red are the losses, and in green are the gains. And what is interesting to see that over time, if you look at this figure here, you can see how most of the changes are actually happening just outside of the border of the indigenous land. Okay? And that makes sense. I mean, that is actually showing that policy could work. Okay? That conservation could work. Okay? That because most of the changes are actually out. But you still have changes inside. Okay? Very small changes that are spread all over the places. Why? This could be selective logging, or what some of our colleagues who are actually working in this area explain us is that what they notice is a mortality in the forest due to a series of droughts. You know, if you only have one drought, it's okay. But if you have repeated droughts over time, then vegetation starts to be affected and start to die. And so that's what they think is happening actually in this case, where you do have sort of spread losses here and there. And just to give you, to show you that figure in a different way, what I'm showing here are, for that region, I'm showing the losses of biomass from deforestation, the red line, and as you can see, it's very, very small. The losses from deforestation are small. But then if I add the losses from degradation, and I do the total, the black line is telling you what it is. And in this case, it's almost 5 times more. Okay, so it's maybe all the changes that we see, all the losses are mainly due to degradation. And it makes sense, it's a protected area, right? You don't really want degradation. So we do have the same data set from Mexico. So for Mexico, there is a data set that is showing biomass change between 2003 and 2014 at the annual interval. How good it is, you tell me. Okay. But before even thinking about showing this, we of course try to have an understanding of if it makes sense or it doesn't make sense. I mean, is it working or not? From what we could see, actually, it does work. Okay. Now we have been mainly focusing on the Yucatan area, and there we can see a lot of changes. I mean, over time, there are a lot of changes. Yesterday, some of other colleagues pointed out to us that this region here, it seems to have a lot of changes, when in reality, there should not be. Well, then, because of that, yesterday we started to look at higher resolution data here, and actually there is a lot going on there. There is a lot of disturbance. There are many roads, many little fields here and there that are popping up. And then we also heard that this area is very difficult to access, so that no one really knows what's happening there. So this type of information could also just be a way to sort of prioritize attention on, okay, so what's going on in the country? I mean, do we know? Did we expect this? No. So should we try to find out why? I mean, what is happening there? It could provide like a layer of information, sort of a verification type of information that you can combine with the INFIS data. But also it could provide you a way to report on losses and gains. Okay? So just for curiosity, so is the countries a source or a sink? Right? You can come up with this type of information. And what this plot is showing is in red are the losses from deforestation. In green below here are actually the gains, so the forest that is regrowing, how much the forest is absorbing in terms of CO2, and so how much biomass is growing. And the blue line is the net, is the difference between the losses and the gain. And so Mexico, after 2013, 2012, is actually a sink. I mean, it shows up to be a sink, meaning that the losses are smaller than the gains. Okay, it's gaining more than what it is losing. And I think if I remember, this is consistent with the estimate from the INFIS data, where the country is actually a sink, is not a source. is not a source. So the advantage also of this is that it's free. I mean, it's free. No, in one way it is free because the data are free. Once you learn how to run the procedure, the computer will do it. Okay. Now, the other things that I want to say is that this was done with no data from Mexico. Okay, this has no field data from Mexico. So what we are going to do as part of MRED and what Wayne showed this morning is that we are going to replace the LiDAR, the space sensor LiDAR, with the airborne LiDAR that Wayne showed. Airborne LiDAR data that has been calibrated with data from Mexico. Okay? And then redo the entire exercise. Wait, are we going to do it or are we just, we're going to do it? No, don't joke. I wanted to do it, but I was not sure if actually is it a plan or not. And so then that is going to be sort of what I would say more reliable product to use because in that case it's based on Mexico data, and not only, but it's based on airborne LiDAR data that will improve the calibration of the model. Okay. Now, for the Yucatan Peninsula, we try to do this with Landsat. So we replace models with Landsat data, and we try to derive the changes in biomass for each 30 meters pixel. Okay. So I'm going to show you some examples of this exercise. Here is a region sort of in the southeast. Again, the color scheme is always the same. So losses in red, gains in green. As you can see in this case, you have few losses and a lot of gains. Okay. Now, if we overlay Matanzan data, just for curiosity, you do get quite a lot. They are quite consistent, but you do have many losses that are actually not identified, and that totally makes sense because maybe it is not deforestation, right? So this is a high resolution image of the area that we have been looking at. Okay, so those places have been losing forests at some time, right? All the rest is really forest. So as you said, you expect that all the rest is mainly growing because it is forest. And so if we overlay the losses, right, you can see how they match pretty well with where forest is not there anymore. Okay. And then you have sparse, sort of a little bit here and there, that could be just small losses due to many reasons. Okay. And then you bring in the gain, right? And you see that actually the gain is mainly in the forest. Okay? We have no gain where there is agriculture. Okay? No gain for the fields. Okay? So this is a type of information now that you can have even at the Landsat scale. Okay? And think about that. This is 1 kilometer. So this is about like 6 kilometers. So it's a pretty small area. So you can have a lot of information. And again, then for each pixel, you have information on what the carbon density is doing. So you can estimate the gains, the losses, different type of loss. And then because it's sort of a high resolution, you can generate those plots for each municipality, for sure for each state, but even at the municipality level, if you want. Okay. And what we are doing now actually is that we went back and we processed the data from 1985 to 2015. So we are going to have a very long time series, and we will be able to really look at what is happening. Okay? So what we hope to do in the future really is to do it for the entire country. Okay. Now we have tested these in the peninsula. That is what we are doing in Emirates. But if it works there, it would be very interesting to expand it to the rest of the countries. For curiosity, if I show on top the biomass change map based on MODIS, this is how it looks like. So the small pixel here are the biomass map from the Landsat data. The big blocks here is the MODIS map change. Okay, you can see that their resolution is very different, but it's getting it. Even at the MODIS scale, actually it makes sense. So what is happening at the MODIS scale is that it does capture where the main changes are, the main losses are. The problem is that in each of those MODIS pixels, you can have gain and losses inside. You can have part of the forest that is losing, part of the forest that is gaining, right? And so what the MODIS data is giving you really, it's a net estimate of the change at each pixel. The loss that you get from MODIS is an underestimate, because in that pixel you could also have gain. And so it's going to show you a loss only in the case in which the gain is bigger than the gain is smaller than the loss. But it could remove quite a lot of loss, right? Because you still have gain. So it is an underestimate. If you're interested in the gross loss or gross gain, you cannot really do it with MODIS. But if you're interested in the net, okay, what is the net value? Then you can do it also with MODIS. It's just that from a visual point of view, it's not as nice as the Landsat data. But in terms of values, actually yes, because what MODIS is giving you is just the total in each of those big blocks. Okay? So to report at the state level or at the national level, why not? So this is the area that we were looking at, and so it's very difficult to actually validate this biomass change. Think about how difficult it is to validate just the biomass of one time. Okay? But then now you need information of the change, so you need permanent plots, okay, over the same time period, and if you work with MODIS, it's very difficult because those pixels are way much bigger than a field plot. And so depending where inside of the MODIS pixel the plot is, could completely not make any sense, right? Because we saw that inside of each pixel there are gain and losses. So where is the plot? Is it the gain or the loss? And it becomes extremely difficult. Well, we were able to find a data set, again in Brazil, where they ran a control experiment with fire, where they burned. So they took an intact forest, Okay, here on the right. And then they burn different portion at different interval of time. And they did this for a few years. And as a result of that, it is still forest, right? But as you can see, it's not as dense as it was before. So there is a biomass loss. And every year they go in and they actually measure in the field completely the area and they report what the biomass is. Because those are few kilometers wide, it was possible to compare with the MODIS data. Okay? And this plot is showing the comparison between the measurement in the field, that is the dash line, and the estimate that we get from the MODIS data. And as you can see, the annual sum of the losses is very consistent with what the field is reporting. Okay? We do have a little bump here in the field, and actually that is it's a change in the measurement in the field that they did for 1 year. This is run by Paolo Brando, who is a scientist who works with fires and droughts. But so we were quite happy to see this because even in MODIS data, you can see that we do definitely capture the trend, the direction of the change. Yeah, so this is the same plot. For the games, what we try to do is that, well, what if we look at plantations? You know, by definition, a plantation is expected to grow. That's why they do it, right? So the WRI, the World Resource Institute, put together a sort of a map of plantations for some countries. So we took that map and we looked at the MODIS data for the regions where they had identified the plantation. As you can see here, those are polygons that they match exactly with the biomass change map, showing that in those polygons where WRI is reporting plantation, our map is actually green, showing that there is a gain. And the type of gain that you get is something like this. It's very noisy, right? But at least you get the trend right. Okay? So that's it. Yeah, so I think I would be interested to sort of hear from you if if this data was actually good, how could that help you? You know, I mean, should we work in making this data better, or for you doesn't it's not something that is going to help you? But before we go there, maybe if there are any questions about this. I mean, I know that it is a lot, you know, it's a lot of things, but.
Bueno, me quedó la duda de este mapa de biomasa.
You speak fast, I
Este mapa de biomasa trabaja bien para las zonas templadas y áridas, o la parte del ejercicio de solamente en áreas tropicales hay como el mapa de masa.
Try it.